Chapter 3, Part B, Mechanical Properties of Materials. If you remember in chapter 3, Part A, in last part, we talk about the Hooke's law and Young modulus within the Hooke's law. Let's have a brief review on that, and we'll come back to the rest of the material of today's talk. So as a reminder from part A, in 17th century, Robert Hooke discovered that there should be a linear relation between a stress and a strain, and almost a century later, 100 years later, it was Thomas Young, another British scientist, who discovered that linear relation is nothing but modulus of elasticity, and after him it called Young's modulus. And represents by capital E, and stands for Young's modulus or modulus of elasticity. Now just consider if you squeeze a material in a compressive test, or otherwise if you pull a material in from its original shape. So in either case, it just, for example, in second condition, it just the length is increased, but the size should decrease because the mass remains the same. It was Simon Denis Poisson, a French mathematician, who discovered this relation between lateral strain to longitudinal one, and that's nothing but nu. He defined it by by nu, and that's nothing but lateral strain to axial strain. So, and the negative indicates that if a material goes by an increase in a direction, it should goes by a decrease in other direction. So if you pull the material from the sides, it should decrease in the other sides. And this equation relates the work of all those three scientists. It relates the Hooke's work by having E, and at the same time it's having the Young's modulus, which is works of Thomas Young. G is a rigidity modulus or shearing modulus, which is again another form embedded in another form of Hooke's law, and nu is a work of Poisson. So this equation connect those three scientists with each other. That's the interesting part of it. And Hooke's law has a normal form and a shearing form. So in normal, it's normal stress equivalent of modulus of elasticity times normal strain, and in shear stress is equal to rigidity modulus time shearing stress. A graph shown here, it's a strain energy versus sigma stress and strain diagram, which shows external work goes to internal work. So W is just, it's transferable to U, which is the strain energy. And the area under first region, as we talked in part 1, area under elastic region is called represented by UR, and it stands for Modulus of Resilience, and that's a modulus that shows how a material is a resilience. And U is nothing but a half of sigma squared over modulus of elasticity. Another term here is modulus of toughness. The whole area under sigma stress strain diagram stands by UT, total U, and that's nothing but the toughness modulus, and it shows how tough material is. As you can see, by adding the carbon content to a steel, the both uh, resilience modulus and toughness modulus increase by the increase in the area under first and the whole region. This table shows different properties for different materials. For example, if you go by a steel, a structural steel A36 in for example in US customer unit, in modulus of elasticity of a structural A36 steel is nothing but 29 times 10 cube KSI, and Poisson ratio for that is 0.32. We need this kind of table to get some properties of material in problem solving. Let's solve a problem here. So in example 1, there is a bar which made of a steel A36 steel and happen to handle a pulling force of 80 kN at both ends. We are going to determine the change in length and also change in cross-sectional cross-sectional area. So first of all, from the table we do know the nu of a 36 steel is 0.32, which is provided within the table, and that's in almost any engineering textbook you will find that kind of table. And the very first part for solving this kind of problem is calculating the normal stress. So the normal stress within this bar is nothing but normal force, axial force over cross-sectional area, which is this area, 100 millimeters times the thickness of the plate, which is 50 millimeters. Convert that to meters, 18 times 10 cube Newton over this area. It gives you the numeric value of 16 megapascal, or 16 to 10 6 pascal. From the material properties, you can also check for a modulus of elasticity of steel. Our problem is in SI units, so just go for SI, that's 200 gigapascal. And as soon as you know them, you can easily refer to Hooke's law, and it says sigma is equal to E times epsilon. So epsilon is simply sigma over modulus of elasticity. We calculate sigma from previous step, which is 16 megapascal, over modulus of elasticity, which we observe it from the table of mechanical material properties. That's 20 times 10 to 9 pascal. And if you do the math, it gives you 18 10 to negative 6 millimeters over millimeters. Epsilon is a dimensionless value. If you want to know how much is the change of the deformation, the axial elongation would be delta is nothing but epsilon times original length in that direction. So epsilon z, delta z is epsilon z times length in z direction. We just calculate epsilon z times 1.5 meter, which is the length in z direction, and it gives you delta z 120 micrometers. Using Poisson equation and knowing nu is 0.32, it gives you epsilon x equal to epsilon y, and that's a negative nu of steel times epsilon z. And by doing the mass, it gives you epsilon x equal to epsilon y, and that's a negative 5.6 micrometers over meter. Again, epsilon is a dimensionless value. Now, when we know what epsilon x is, what epsilon y is, the change in dimensions of cross-sectional area of would be delta x, which is epsilon x times length in x direction, epsilon y, it's delta y is epsilon y times ly. If you replace the numeric value, just epsilon x times the length in x direction, and the delta y is epsilon y times length in y direction, which is 50 millimeters over here. Doing the mass gives you the numeric value of both in micrometers for elongation. In another example, we can look at a bar which is a cylindrical bar with a diameter of 16 millimeters, happen to handle a 12 kN pulling force outward. If we do know the increase in length is 300 micrometers and a decrease in diameter of 2.4 micrometers due to this 12 kN axial force, we are going to determine the modulus of elasticity and also the Poisson's ratio. So it's just vice versa of the process is vice versa of previous problem. So first part is calculation of the area. Area is pi r squared, pi 8 to 10 negative 3, all in parentheses squared, gives you the area. Sigma is force over the area, 12 k Newton over the cross-sectional area, which we calculated, gives you 59.7 megapascal. As soon as we calculate this part, and then we know epsilon x is delta x over L, so 300 over 50 gives you, and also epsilon y is delta y over L. So these are from the problem statement. We know increase and decrease from the problem statement, and if you replace that in their formula, gives you the numeric value of epsilon x and epsilon y. As soon as you have epsilon x and epsilon y, by applying Hooke's law, we calculate sigma in previous steps. Sigma over epsilon gives you the modulus of elasticity, which is what we are looking for. So epsilon is sigma in x direction over epsilon in x direction. 59.7 megapascal from previous slides over 600 to 10 negative 6, which is epsilon x over here, gives you the numeric value of 99.5 gigapascal. And by knowing nu is negative epsilon y over epsilon x, and if you replace the numeric value, so negative 150 comes from here, 60 comes from here, and it just gives you a Poisson's ratio of 0.25. So E stands for elasticity modulus, and nu of 0.25 stands for Poisson's ratio. Thank you.